Everyone. So I am, as I mentioned in your group, that I am going to uh, release some more videos regarding the important contents in connection to the vibration, which you have already discussed in the class also. But I thought that as some of you may find it difficult, so it's good to have a recap on the things. Now, torsional vibration I have elaborately covered in the class, but considering the importance of this topic in your exam, let us look into the things once again. So this the figure of a shaft which is having a disc at its free end, and the shaft is fixed at one end. Now if I see the front view or view from the bottom, we'll see like this, which is the disc view. Okay, behind that the shaft is attached, which is fixed to one end. Now I know that the moment of inertia of the shaft is I equal to mk square, where k is the radius of gyration. Now what will happen if I give a small rotation to the shaft disc? Due to the stiffness of the shaft, this will try to restore itself, and in that way the torsional vibration will continue. Now see, here, unlike the spring, we are considering the stiffness Q is the torsional stiffness. In place of K, we are considering the Q as the torsional stiffness. Now in case of torsion, as per the knowledge of our strength of materials, we know that T by J equal to G theta by L. G is the modulus of rigidity and J is the polar moment of inertia of the cross section of the shaft, means the this one, okay, which is of length L. Now T by theta, obviously see from here we are getting T by theta equal to Gj by L. Now T by theta is that torque required is the stiffness of the shaft, that is the torsional stiffness, means torque required for per unit deflection. Like the spring stiffness, that is the force required for per unit of deflection of the spring. In such way, per unit angle of twist is the expression T by theta, which is Gj by L. Now that is the standard relation, means in that way we are getting the stiffness here. Okay, now if we get the stiffness from there, we can get other values also, but by knowing the inertia we can find out the frequency. Okay, means yeah, unlike the spring, if we get the k value and the m value, we can know the omega value, root under k by m. From omega we can find out the frequency value also, isn't it? So let us look into one problem. Please remember that this is the torsional vibration problem. Now a shaft of 100 mm diameter, the dia of the shaft is given, which will help you to find out the polar moment of inertia J. Circular shaft is there, so pi d to the power 4 by 64. Okay, now that is about x-axis or y-axis. So if I want to find out the moment of inertia about the centroidal axis, then it will be pi d to the power 4 by 32. Now apart from that is of length 1 meter, and one end is fixed, other end carries a flywheel of mass 1 ton, 1000 kg. Okay, the radius of gyration of the flywheel is 0.5, though k is given, so we can definitely find out the I. Find the frequency of the torsional vibration. Frequency निकालने को बोला है, G equal to 80 giganewton. In some place we consider it as G, some place we consider as C, doesn't matter. Now J, as we have said, the centroidal moment of inertia for torsion, so pi d to the 4 by 32, and we got this value. Okay, now Q equal to, that is the torsional stiffness, Cj by L. Here I have shown it by G. Now I am representing the same thing as C. I could have written G actually, where I have written G. Now see that value, I have not shown you the detailed calculation, so it is 785.4 Newton meter. Okay, now you see that is the torque per unit torsion, per unit rotation. Okay, so that's why the unit of torque has come here, into 10 to the power 3 is there. Okay, now L equal to 1 meter, that is clear. Now I of the disc, I have calculated 1000 into 0.5 square, that is 250 kg meter square. Now frequency, before going to frequency, let us see time period. If I know the time period, if I know the k and m, or stiffness and the inertia, torsional stiffness and inertia, then I can find out the omega. From omega I can find out the tau equal to 2 pi by omega. So frequency equal to 1 by tau, which is 1 by 2 pi into omega. So 1 by 2 pi into root under k by m. So in case of torsional frequency, it will be 1 by 2 pi Q by I. Okay, that's what we have found out. Frequency equal to 1 by 2 pi root under Q by I. And already we know the Q value, which you have just calculated, this one, and I is the disk, that is the moment of inertia of the disk. Okay, Q by I, that is the, and in Q the J was for the shaft itself, for the shaft material. Okay, so 8.29 hertz, that is the cycle per second. Okay, now if they ask you that RPS or RPM, then you have to, that is the this much of revolution or cycle per second. So if they ask for the RPM, then you have to multiply by 60 to get the RPM value from the frequency. Okay, now that is for the torsion what we have discussed. Now see, if that is for transverse vibration. Transverse means kaisa hai? Means either in this way, let me draw it, either in this way, in this way, this way, this way. If it vibrates, then that is the transverse vibration. And if they say about the longitudinal vibration, it will be like this way only. Okay, so in case of transverse vibration, obviously if I consider it as like a cantilever, one end is fixed, in the other end the mass is fixed, so the deflection will be WL cube by 3EI. Now we know that for the, from the knowledge of our vibration, we know that omega n can be written as root under G by delta. G by delta, where delta is the static deflection. In such case also, whenever there is a cantilever like a thing and we are having a mass at its free end, and if it is in the transverse direction, the deflection will be WL cube by 3EI. That's what I have written here. Okay, so in case of transverse vibration, frequency will be 1 by 2 pi root under G by delta. In case of omega, root under G by delta. Delta ST I have written, and for the T is denotes the transverse vibration. Okay, so by knowing this delta T for the transverse, we can know loading at free end. And regarding the at different types of loadings, what will be the deflection, I might have circulated one thing in the group also. Okay, now if this is vibrating in the longitudinal direction, as I have drawn the figure here, let me change the longitudinal direction, means this way, this way. Okay, in such case, the what will be the deflection? Deflection will be WL by AE, right? And that has come from the stress by strain. W by A is stress, E equal to stress by strain, and delta L by L is the strain. Okay, so from there we got the strain value, that is the change of deflection, how much deflection it has taken, WL by AE. So from there we also can find out 1 by frequency equal to 1 by 2 pi root under G by delta. L denotes the longitudinal deflection. So it depends that if they are asking for the transverse or longitudinal, depending on that you are going to find out the delta. Okay, delta T or delta L, and you simply have to substitute it in the frequency formula. That's it, and you can get the value. Okay, so in case of torsional, this relation will be just, you have to remember that Q equal to, from here you can also find out T by theta equal to Gj by L, and from there you can find out the torsional stiffness. Once it is obtained, you just have to know the moment of inertia of the disk or the thing which is attached on the free end. From there you can find out the frequency. Okay, please note the question carefully, because if they ask you for the RPM value, then you have to multiply with the 60. Okay, now that is done for the torsion. But in the torsion chapter, the next topics were the torsional equivalent shaft, 2 rotor systems, 3 rotor system, then finding out the nodes. All these things we have covered. Okay, so you just have to go through the class materials, things will be more clear. So obviously you will listen this video also. Now see, we are coming to another important topic, that is the torsionally equivalent shaft. Torsionally equivalent shaft means, suppose a shaft which is subjected to torsional vibration, now it is having different dia at different lengths. Different dia at different lengths. Under this scenario, what will be the torsionally equivalent shaft? Means I am considering the same shaft, it will have the same properties, but the thing is it will have a uniform dia throughout, unlike this one where the at different length, dias are different. I want this to have a uniform dia. Maybe the length will change, but I want it to be torsionally equivalent. Means if I apply in that new shaft the amount of torque, same amount of torque, the twist should be same. The twist should be same. Okay, so that is what at the beginning I have written, that torsionally equivalent. Okay, means if I apply the same amount of torque, the angle of twist should be same for the equivalent shaft and for this shaft also. So here you can see for torsional vibration two opposite torques will be provided, so that's why these arrow directions are different. And I can see that at different lengths, L1 is having the D1 dia, L2 is having the D2 dia, L3 D3 and L4 D4 dias. Okay, so I have written at the first line, terms will always give you the idea to address any related problems. Okay, so यहाँ पे सिर्फ आपको एक ही चीज़ याद रखना है कि सभी का ट्विस्ट जो होगा ये सब, इफ़ आई अप्लाई ए टॉर्क हियर, दिस विल रोटेट एट डिफरेंट एंगल. इसका स्टिफनेस थोड़ा डिफरेंट होगा, इसका डिफरेंट होगा, तो दे विल रोटेट एट डिफरेंट एंगल्स, बट द टोटल एंगल ऑफ ट्विस्ट विल बी द सेम फॉर द टॉर्शनल इक्विवेलेंस. So obviously I understood one thing, that the theta is a important parameter here. Okay, so that's why in the next line I have written, each part of the shaft will provide different torsional resistance. Obviously their torsional stiffness is different, so they will provide different torsional resistance. The total rotation will be the summation of all the rotation of individual parts. तो मुझे हर एक थीटा 1 थीटा 2 सारा निकालना है, सबका ऐड करना है, then it will be a total twist. Then we shall make it a equivalent shaft. Okay, so we already know that Q equal to Cj by L. Q equal to T by theta equal to Cj by L. From there, theta equal to, I can write TL by Cj. TL by Cj. So for individual part, the rotation we can write theta 1 equal to TL1 by Cj1, TL2 by Cj2, TL3 by Cj3 and TL4 by Cj4. So J1, J2, J4, J3, J4 are nothing but the cross-sectional moment of inertia of each of these parts. Okay, so obviously about the centroidal axis, so it will be pi, for the J1 will be pi d1 to the power 4 by 32, J2 will be pi d2 to the power 4 by 32, and similarly d3 and d4. Okay, thus D is the dia of the equivalent shaft. So let me assume that dia of the equivalent shaft is G. Okay, let us consider the equivalent shaft is equal to any of the following existing diameter. So it is normally a common trend that whenever we are considering the equivalent shaft dias, I consider that okay, any of the diameter will be the throughout the length. Means in this case, let us assume that in the equivalent shaft the dia will be D1 throughout its length. Unlike here D2, D3 and D4 has appeared, I want it to be D1 throughout its length, whatever length it will have. Okay, so that length actually we are going to find. So from here you see the torque applied was same throughout the shaft, सब में एक ही torque apply किया गया है. So if I write the theta, which is theta expression के TL by Cj. So TL is the LE is the equivalent shaft length, C and J is the equivalent shaft polar moment of inertia. Okay, so I am adding all these angles, theta 1, theta 2, theta 3 and theta 4. So this relation has come. Now you see T is same throughout, C is also getting cancelled out. So LE by JE. JE is nothing but pi d to the power 4 by 32. So that I can say that pi by 32 is also getting cancelled out from all the terms. So it is LE by d to the power 4 equal to L1 by d1 to the power 4 plus L2 by d2 to the power 4, L3 by d3 to the power 4 and L4 by d4 to the power 4. Okay, so if I consider that okay, equivalent shaft will have the diameter equal to d1 throughout, so in place of d I shall substitute the d1. Okay, so d1 if I substitute, then equivalent length will be L1 plus L2 into d1 by d2 to the power 4 plus d1 by d3 to the power 4 and d1 by d4 to the power 4. And this is a very important expression, this one. Okay, this one is a very important expression which is giving you the length of the equivalent shaft. So if they ask you that okay, this shaft is having these two defined diameters or these three defined diameters, and I want this to be having this diameter throughout. In that case, you are going to use this formula, and that will give you the equivalent length of the shaft. Okay, and this can be used for find out the equivalent length. Okay, just you have to remember this one. Okay, here d1 was used. If they ask you for d2, then it will be l1 by d2 by d1 to the power 4, that plus l2 plus l3 d2 by d3 to the power 4 plus l4 d2 by d4 to the power 4. Matlab, we have to decide that which dia I want it to throw out. Okay, so that is one thing. And after that, we have covered the Duncan-Lewis method also, where this particular formula was derived. This formula was derived. Okay, so and in that method, this is an approximate method where we have found out the frequency of shaft under different loading conditions. Suppose that shaft is subjected to some point loads. So in that case, the frequency will be 0.4985 by root under d1 delta 1 delta 2 delta 3 plus delta s by 1.27. Okay, that is the, so delta 1 and delta 2 delta 3 are nothing but the deflection of the shaft due to these individual loadings, and delta s is the deflection due to its self load. Okay, so that's what I have written. Delta 1 delta 2 3 are the deflections under different loads condition. It can be different loading condition. So delta 1 can be a offset loading, delta 1 can be a central loading. Okay, delta s is the deflection due to the self weight. So here also I have shown different loading conditions. You see, this loading conditions means delta, you see, offset. So when there is this weight, a point load is acting on the shaft, not at the midpoint, then what is happening? If the point load having a distance of A and B from both the ends, and this is a simply supported condition where the total length of the shaft is L, and delta offset W A square B square by 3EIL. 3EIL, and EI already you know what it is. Delta C, when it is centroidal, then WL cube by 48 EI. Okay, so that is a simply supported. Okay, now you see with the self weight, when it is the self weight is given, uniformly distributed load is given throughout, then it will be 5 by 384 WL to the power 4 by EI. 5 by 384 WL to the power 4 by EI. Okay. Now W, this is not the, this is the loading per unit length. Otherwise you see dimension here, it is L cube, but it is L to the power 4. That is the W here, small w, which is loading per unit length. Means load per unit length is this W here. Now when due to static loading, and you see when this is the case, when it is simply supported, both the ends are simply supported. Here also is centroidal load. In case of simply supported, it is WL cube by 48 EI. Please note that thing. When the shaft will be fixed at both ends, in that case, if there is a centroidal load, in that case WL cube by 192 EI. WL cube by 192 EI fixed at both ends. This was the simply supported. So these are the defined loading conditions under which the deflections will be defined. So depending on your problem, you'll find out that what sort of deflection it is having. Obviously self weight के लिए यही होगा, WL cube by 192 EI. So in the problem, by studying the problem, you will understand that what sort of loading is there, what are the defined points, where are the defined points where the loadings are there. So often there may be a centroidal load, there may be offset load, obviously there will be a uniformly distributed load also, and in some case the shaft can be fixed at both ends, and sometimes it can be simply supported. So these things will be mentioned in the question. If it is not there, then it is upon your assumption. Okay, now this is the condition. We shall try to cover one problem on these things, okay, in the next video, because this video is becoming long, and if it is very long, then it will lose interest to lose your interest to understand. Okay, this is the Duncan-Lewis formula. You have to remember this for frequency, and this is used to find out the frequency for the shafts at different loading conditions for the transverse vibration. Okay, and this is the equivalent length of the shaft for torsionally equivalent shafts. Okay, with this I am stopping here. I shall cover this one problem on this dunkerless method in the next video.